Alright, let's get started. This is the third video I've made in preparation for your guys' fluid final, ME211 fluids final. Sorry if you hear a bunch of weird noises at my feet. That's my dog. He found a squeaky. I punctured the squeaky so it doesn't squeak, but it still makes weird squelching noises. So if you hear that, believe me, I don't like the sound either, and I am sorry. Anyways, let's talk about stream functions, and specifically deriving stream functions, just to explain it. If you don't like math, this is going to be a rough one. But if you do like math, this might be really fun. Anyways, so some backstory real quick. We are talking about the continuity equation for incompressible flows. In essence, this is something that you'll use a lot. This is the whole point behind stream functions and potential flows, is that they're wanting to solve this equation. So del dot v is equal to 0. So basically mass can't be made or taken away without some kind of source or sink inside a control volume. As you can see here, you don't have to memorize these, but these are essentially this is called the divergence in these different coordinate systems, right? So to use potential flows and stream functions, you typically have to have 2D flows. There are 3D extensions, but we are limited to 2Ds here. So this is what this equation is. So what is stream function and potential function? So in essence, if we go back, or if we're looking down here, this del dot v, we are going to have two components that we have to solve for, and that's kind of a pain, right? So we want to have some kind of scalar function, psi or phi, e. I could pronounce it as phi. I don't know. Some people who are in Greek life are gonna get mad at me. Whatever. But notice we have the Laplacian, right? So it's similar to this, where we only solve for one variable, one function. So therefore, we have lowered the number of variables we have to solve for. Okay. Here is a little diagram of the difference between a potential function and stream function. Potential functions are given by the negative gradient as you move through. And then stream functions, as they kind of sound, imagine you just ride along the stream function itself, and that kind of tells you how the flow develops. Okay. So we are essentially going to derive how we get these stream functions. So in essence, the way that you want to think about how a stream function came to be. By the way, stream functions and potential functions must satisfy this. This is called a Laplacian. They must satisfy this equation. To be quite honest, the why that needs to happen and the relation between stream function and potential functions are way beyond the scope of this course. But if you really want to cook your noodle, look up the Cauchy-Riemann equations or Cauchy-Riemann conditions. And I'm sorry for whatever you come up with and the ensuing headaches. Maybe do that after finals. Anyways, okay. So the whole reason we choose the stream function is that it quote-unquote zeroes out the continuity equation. So you could see here, based on how I chose u and v, when I try plugging that back into the continuity equation, so this for Cartesian, for example, you could see that it just makes it 0 is equal to 0. Okay. So that's the whole reason we choose the stream function. And then the potential function, where does this come from? There is a condition for irrotational flows. Okay, so basically it has 0 curl. If you try doing the math for a 2D flow, so in other words, u and v do not have components in the z direction, you will find that in order to make the curl 0, you have to define phi as define u as del phi del x and v as del phi del y, and it will make the curl for irrotational flow go to 0. So that's basically where these came from. You could have honestly just skipped this slide and that would have been completely fine. Probably would have confused you less, but I at least wanted to show where these came from because I never understood stream function. Potential functions always made sense to me, but never stream function. So anyways. Key thing here is that these are two-dimensional. It has to be two-dimensional, right? We are working in 2D, no 3D. So, for example, here it is in cylindrical coordinates. You have like 3 different flavors. You have 3 different coordinates, so there are 3 different ways you can combine those. So you have here, if we just had VR and V theta, this is how you look at the stream function. It's good practice, honestly, or maybe a nice little brain teaser. If you try to prove yourself throwing this into the divergence equation, that it'll be 0 is equal to 0. And this is how you get the potential function. This one is if you have your velocity components are only in R and Z. And once again, here is the respective stream functions, potential functions, and then lastly, theta and VZ. Okay. So here was the problem we worked on in class. Velocity components for an incompressible plane flow are this stuff. A and B are just constants, they're just numbers, don't worry about them. And determine the corresponding stream function. Okay? So this one's actually pretty straightforward. For the R and theta, we can see here that we're going to use this equation, these 2 stream functions. And we just go through and take the indefinite integral for these 2. Also, sorry, my dog's barking is coming across the mic. Something of note, you'll notice that we took an indefinite integral, so we will have a constant associated with that integral. But it will be constant with respect to that variable. So for instance, this f of r, if I take a derivative of f of r with respect to theta, we know that this term will just go to 0, right? So therefore it is constant with respect to theta. We have with our other equation on the right hand side, notice how I tried to split this up, that we have this equation plus g of theta. So this is a constant with respect to r. Both of these have to be the same stream function, right? That's just how these stream functions work. You can see that VR, V theta, they're both related somehow to some stream function psi. So these equations need to be equal to each other. So what I do is just set them equal to each other. You'll notice that some things cancel out, and I'm left with a theta plus f of r is equal to g theta. So some function of r and some function of theta. And I get to choose what those are. So to make it match, I just said f of r is 0 plus some constant c. And then g of theta is just a theta plus c. Why did I choose these c's? We go back based on how the stream function is defined. For different values of c, you'll notice that you rely on different stream lines. Okay, so that's why we have to choose. And we also did an indefinite integral would be the math answer. But the physical answer is that those different c values will let you apply on different points or different functions. So we just slap in c values, and we see that we get our final psi value, and we are golden. One thing you must do, you should do this on your exam. This is a great way to check if you are wrong. Throw this back into these equations, right? You have the known value for v sub r and v theta. So therefore, when you take the derivative, you take the appropriate derivatives with respect to this, you should be able to get these values back, or these equations back, right? And that's how you know you did this correctly. But so that ends what we did in class Friday. Let me know if anyone has any further questions. Due to time constraints, I don't know if I'm going to be making more sample problems just because I have a lot of things to do. But maybe I can answer them verbally either in the comments or via email. anyways, best of luck on your finals, guys. It was an absolute pleasure being your TA. And I hope to see you guys around. All right, see you.